All right, well, now we're going to look at writing chemical formulas and how to name them for simple ionic compounds. So remember that elements are going to form these compounds in order to be stable. So the compounds together are going to have very different properties than the elements by themselves. So again, that example of sodium chloride or table salt that we've been talking about, sodium itself is a shiny silver metal. It's very reactive. Chlorine is a poisonous gas, but when you bring it together and you make table salt, now it's something that's very stable. It's stable at room temperature. It's safe to consume. So if we look at the formula that we've written for it, you can see you have Na and you have Cl, which basically indicates the relative amounts of things. We said that you have one sodium and you have one chlorine and they balance each other out. So when we write a chemical formula, you're going to tell both the elements in the compound and then the exact numbers of how many you have. So Na2O, this is actually sodium oxide. This is going to be 2 sodiums, 1 oxygen. If you notice, whenever there's going to be 1, we don't put a subscript. We just write the symbol, and that implies that there was 1. Then you got this, which is called calcium phosphate. We'll talk a little bit about what that PO4 is in coming videos, but that means you have 3 calciums, 1 phosphorus, 4 oxygens. Here, this is called iron 3 oxide. We'll talk about where that number comes from too, but it's just 2 irons and 3 oxygens. And then again, sodium chloride, just 1 sodium and 1 chlorine. So the parts of the formula that you have are your chemical symbols, and then you have the subscripts to tell you how much of each atom you have. So 2 sodiums in this example and 1 oxygen. All right, so things that we need to know when we're going to actually write the formulas for ionic compounds. We need to be aware of what elements that are bonding. So for ionic compounds, it must be a metal and a nonmetal. If it's 2 nonmetals or there's a noble gas involved, then it's not going to be an ionic compound, and we'll actually learn about those later. We then need to look at the oxidation numbers using our periodic table, and then we have to remember that the compounds formed are going to be neutral. So, sorry, this should be a 1 there. So 1 are what elements? So if we look and we see, let's say we're going to react barium and oxygen. If we look on the periodic table, barium is a metal on the left-hand side, oxygen is a nonmetal on the right-hand side. So yes, this is going to be an ionic compound, and we could move forward. Magnesium and fluorine. Magnesium's a metal, fluorine's a nonmetal. So yes, this is going to be ionic, and we could move to step 2. For the next one, sulfur and iodine. Sulfur and iodine are both nonmetals. So this is not an ionic compound, so we don't have to worry about charges or anything, and we'll actually learn about what kind of compounds those are in Unit 4. Strontium and neon. Now this is an example where we do have a metal and a nonmetal, strontium being the metal, neon's a nonmetal. However, neon is a noble gas, and noble gases don't bond, so it's not going to make an ionic compound. So again, that's one where we would just skip. But if we have identified ones that are a combination of a metal and a nonmetal, then we can move on to step 2, where we look at the oxidation number. So again, the oxidation number, or charge that the element has when it becomes an ion, is predicted by just looking at the columns on our periodic table. And this is exactly one of the examples I showed in the last video. So calcium is in column 2, and it's a metal, so it's going to be a +2 charge because it gives away 2 electrons. Phosphorus is in column 5. It's a nonmetal, so it's going to gain electrons to have 8, so it's going to pick up 3 electrons, and it's going to have a -3 charge. So again, these are our oxidation numbers that you should have written on your periodic table, so you can reference them whenever writing ionic compounds. The last thing that we need to know is that compounds are neutral. So ionic compounds, all the pluses and all the minuses are actually going to cancel out, and that's what we're going to do to be able to determine the relative quantities. So here's an example of another example of an ionic compound. It's calcium fluoride, and so based on the formula, you can see that there's 1 calcium and 2 fluorides. Well, calcium has a +2 charge, and fluoride is in column 7, so it has a -1 charge. So overall, when you have 2 fluorides, you're going to end up with a -2, 1 calcium plus 2. The net charge of this ionic compound is going to be 0. So we're going to identify the elements and write their symbols, and then write them with their charges. So we're always going to write the metal first and put its charge, and then the positive charge, and then we write the nonmetal symbol, and we write the negative charge from the oxidation number on the periodic table. Then we're going to move the charges without the sign to become the subscript of the other, and I'll show that in a second. And then the last thing that we have to do is reduce the ionic compound to the lowest whole number ratio. And again, I'll give an example of that. So what we do is we call this the criss-cross method. So if we're going to write the formula for beryllium phosphide, or the combination of beryllium and phosphorus, first we write the cation, so beryllium is a +2, and then we write the anion, so phosphorus is a -3, and then we crisscross down. So the charge of beryllium becomes the subscript of phosphorus, and the charge of phosphorus becomes the subscript of beryllium, and we leave out the plus and the minus. So essentially what we get is Be3P2. 3 berylliums, 2 phosphorus. Let's look at aluminum oxide. Aluminum is in column 3, so it's a +3. Oxygen is a -2. So if we crisscross down, we're going to have 2 aluminums, 3 oxygens, so it is Al2O3. Lithium nitride. Lithium is a 1, nitrogen is a -3. So when we crisscross down, we get Li3, and then N. Remember that we don't have to write the ones, because just by writing the symbol we imply a 1. All right, here's an example where that fourth step comes in, where you actually have to reduce to the lowest whole number ratio. So when we combine beryllium and oxygen, both of them have a charge of 2. Beryllium is a +2, oxygen is a -2. So if we were to crisscross down, you would think that the charge would, or the formula would be Be2O2. But the ratio is 2 to 2, which is the same as 1 to 1. So the last step is to reduce to the lowest ratio that you can get. So they actually just cancel each other out, and the formula that we have is going to be BeO, 1 beryllium per every 1 oxygen, and will balance to have a net charge of 0. All right, to write the names of these things, we always just write the name of the positive ion first. It's just what its name is. Nothing changes. If it's a sodium ion, we say sodium. If it's calcium ion, we say calcium. The second part, though, when we write the negative anion, we're going to change the ending. So we use the root of the element's name, and then we change the ending to IDE. So for oxygen, we would say oxide. For phosphorus, you say phosphide. Nitrogen is not nitride. And some of these are easy. Maybe you've heard of them before. Some of them are a little bit trickier and you're not really sure what the root is. You'll just get to know them as we use them, and I'll correct you if you make any mistakes. Like, for example, sometimes people put nitrogide, like they add in the G there when it's really just nitr and then add the IDE at the end. But you'll get to know them as we use them in class. All right, so just to show some of the examples we went over and the formulas, so you've got lithium nitride, calcium fluoride, aluminum oxide. So the metal name stays the same, the cation stays the same, and then we change the ending to IDE for the anion. All right, in the next videos, we'll get a little bit further into looking at what are called polyatomic ions. So far, we've just been using what are the simplest metal and nonmetals and very specific columns on the periodic table, but there is some more complexity to it, and we will be looking at some more advanced writing of binary ionic compounds.